Okay, we have talked about what is a normalized form and when you are converting from decimal value to a binary. So we have discussed in the previous slide, so please refer to that. Decimal to binary. We have already seen how does 35.7 looks like. So it will be something which is very similar to the signed bit, and this is a 23-bit mantissa and 1 bit, and the rest of the bits are exponents. So E dash, and this is mantissa. So this is what we have already discussed, and this representation can be mentioned it is as normalized if this can be written in binary. 35.7 can be written in binary as 1 point, that is sine multiplied by sine multiplied by 1 point mantissa into 2 to the power exponent, that is minus E dash minus 127. We have already discussed in the previous slides, that is, if you go to this, we have already said plus or minus, that is sine along with E dash minus 127. So we are going to elaborate on this. So let me give you an example. If we have a representation, say this is 0, this is mantissa, say 0 0 1 1 0 0 1 1 0 1 1, something like that, and you have a mantissa, say 1 0 1 1 1 0 1, 3 4 5 6 7 and one more 0. So here this can be converted to exponent as, this is positive, and 1 point mantissa, you are going to write the mantissa as it is 0 0 1 1 0 0 and so on, into 2 to the power this value. So this value will be 2 to the power 2 plus 0 1 2 3, that is 8, plus 16 plus 32 plus 128. This value I'm going to take. So totally it will be around 128 plus 32 plus 16 plus 32 plus 16 plus 8 plus 2. So this is 186. So 2 to the power 186 minus 127. So this is the normalized form. So I can express it as plus 1.001100 something into 2 to the power this will be 59. So furthermore, you can represent this particular mantissa as so this is quite a huge number. 2 to the power 59 is quite a huge number, but still we have managed to express in the binary format. So this is the beauty of taking minus 127. Okay, let me tell you the story about minus 127, why it is a number specifically 127. So 127 is nothing but almost half of 256, that is almost half. I'm not going to exactly divide it. So 256 is this will be with all the ones 1 2 3 4 5 6 7 8. Okay, erase 1. So this will be my 255. So if I am considering all ones here, I am going to take the exponent as 255. So 255 minus 127 will give me 128. So the range is expressed from 128 and up to, if it is all zeros in this case, that is exponent will be 0. So 0 minus 127 will be minus 127. So the range is from 127 to minus 128. So instead of taking from the number line 0 to 128, what I'm going to do is I'm going to extend it both the sides and consider from minus 127 to almost plus 127 to 128. So instead of taking this much, I'm going to consider this much. So this is what the story of minus 127. In other words, if I want to specifically choose the number from both the sides of 0, that is from both the sides of the number line, so this is a better range than this. Here only the positive that is values above 0 are considered, but in this case value below 0 is also considered, that is the half below and half above. That is the story about 127. That is what we have seen in single precision number, and the same thing goes with double precision number. What we are going to do is increase number of bits. From 32 bit we are going to increase it to 64, and 8 bit notation to 11 bit, and the sign bit is as it is, that is 1 bit. You don't need much more bits to denote the sign, that is 1 or 0. So since it is a double precision, what we are going to do is increase the range, that's all. Plus or minus 1, that is 1 point mantissa into e to the power e dash minus, instead of 127 I am going to just simply write it 1023. As you know, 1023 is nothing but 2 to the power 10 minus 1, 1024 minus 1. Here it is 2 to the power 127, that is 128 minus 1, that is 2 to the power 7 minus 1, instead of 2 to the power here 8 bit it was, so 2 to the power 8 minus 1, and here it is 2 to the power 11 minus 1. So it is quite practical to use a heavier precision, that is a double precision, when you are dealing with 64-bit machines. Okay, now the point is, why do we want to consider the normalized form? What is an unnormalized form and a normalized form? Simply understand that normalized form is 1 point mantissa. Whenever you are taking 1 point mantissa, it is normalized form, and when you are taking 0 point mantissa or any other non one number, it is a unnormalized form. So practically we are going to use a normalized form. I'll tell you why. Because when you are dealing with computers, every protocol has to be same, that is every place where you are going to denote a number should be same. So whenever I want to denote any binary number or any decimal number in binary, what I want to do is I want to express it in a uniform format, that is I want plus or minus 1 point something into e to the power exponent. It should not be somewhere it should be 0 and somewhere it will be 1 or something different. So it is preferred that you take a value which is uniform throughout the representation, that is 1 point something. So that is what the normalized form is. So going back to the same way we have expressed this, I am going to tell you how this is expressed in a normalized form or the unnormalized form. So coming here, so since it is 0, it is going to be positive. This is my exponent, so 2 to the power 0, 2 to the power 1, 2 to the power 2. So 2 to the power 2 is 4 plus 1 is 5, and the MSB is 1. So 0, 1, 2, 3, 4, 5, 6, 7. 2 to the power 7 is 128. 128 plus 1 is 129, plus 2 is plus 3 is 131. So 131 minus 127 will give me 128 plus 2 to the power 0 is 1 plus 2 to the power 2 is 4. So 133 minus 127 will give me 6. So that is why the exponent is 6. You are going to write the mantissa as it is. What about in unnormalized form? Unnormalized form is also the same thing. You are also going to represent the sign bit with 0, and the sign bit with 0, so it is positive. So 0 point, the mantissa is written as it is. Let us see how the exponent is written. So it is nothing but 2 to the power 7 is 128 plus 2 to the power 3 is 8. So 128 plus 8 is equal to 136 minus 127 will give me 9. So this is how 2 to the power 9 is written. Alright, so I believe this is clear. So this is the IEEE 754 representation of floating point number, sign bit, exponent and mantissa. Exponent, if you are writing from decimal to binary, you are going to add 127, and if you are writing from binary to decimal, you are going to simply subtract 187. Alright, so this represents my the same way how there is a decimal point, and left to the decimal point how it is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3 and so on. The same way it is in the right hand side, but it is in fraction, that is 2 to the power 1 by 2, 2 to the power 1 by 4, 2 to the power 1 by 8, 1 by 16 and so on.